Hello, and welcome to a lecture on stationary phase evaluation of physical optics problems. My name is Steve Ellingson. Here's an overview of this lecture. First, I'll remind you of an example that we did in a previous lecture, that of plane wave scattering by a perfectly electrically conducting cylinder. And we used that as a demonstration of the efficacy of the physical optics method. In this lecture, we'll be talking about the stationary phase method. And this is a technique for reducing the physical optics integral to a closed form expression. So quite literally trying to avoid integration by somehow manipulating the physical optics integral into a closed form expression. Along the way, we'll encounter this thing called Fermat's Law. It will turn out that this method of stationary phase can be interpreted as reflection. Then we'll do a comparison of physical optics, that is the traditional way by integration, versus stationary phase evaluation. And then I'll make some concluding remarks. Okay, so here's the problem we worked in a previous lecture, that of a uniform plane wave incident on a perfectly conducting cylinder having radius A. And this is a two-dimensional problem, and we worked it as a two-dimensional problem. The physical optics solution that we obtained is shown here. It's quite simple. It reduces to a bunch of constants, a cylindrical wave. And remember, this is the far field solution, so we should expect to see such a thing. And then the integral, which provides the scattering pattern. So by stationary phase evaluation, we mean something very specific. What we do is we look at this integral, and we notice that it has this form where Ka appears in the exponent of the exponential. And if Ka is large, what is happening is that this phase factor is spinning relatively quickly. What do we mean by that? We mean that e to the plus j anything is this vector which points at different directions and has unit magnitude, and it's spinning around, right? If Ka is large, then this spins around a lot, right? If Ka is small, then this might only rotate a quarter of a turn. But the kind of problems we're interested in, where Ka is large, this spins around pretty fast. In contrast, this part here varies slowly with phi prime, with the variable of integration. So we have a part here that's changing quickly, and changing quickly in a way that is simple to describe. It's just this rotation. And then we have a part here that's changing slowly. So this is really telling us something. If I would look at just this integral, right, I'll take this integral by itself and now consider how I might more efficiently compute this. Here is this slow moving part, this slowly varying part. And then here is this rapidly varying part. And it's not just rapidly varying, it's rapidly varying in a particular way. It's spinning around as I've shown here. So I'll call those two parts f sub m and f sub p. So now the whole integral is an integral over the product of those two things. Now, stationary phase evaluation of the physical optics integral. Well, it goes like this. Let's just consider a particular situation here. In this particular situation, the distance to the field point is 1,000 wavelengths, so well into the far field. The angle to the field point is 135 degrees. And let's choose 10 wavelengths for the radius. And then let's see what these two functions, f sub m and f sub p, look like. Well, here's a plot of phi prime, the variable of integration, relative to the functional values. For f sub m, for the slowly varying part, here is what we see. It is in fact slowly varying with phi prime. But the quickly varying part, f sub p, is this phasor that's spinning around. And here I'm just plotting the real part so you can see it as a sinusoid. But what you see is it's spinning very, very, very quickly in this region, and it's spinning very, very quickly in this region. So it's not hard to see that we're going to end up with a lot of cancellation in this region and a lot of cancellation in this region, and most of the integral is really determined by what's going on in this range. Here I'm just saying it in words. In these regions, the rapidly spinning phase with only a slight variation in magnitude, so negligible contribution to the integral here, and then nearly the entire integral is determined by this region around this one point, and we can see here it's about 157.5 degrees, and that's what we refer to as the stationary phase point. So the idea in stationary phase evaluation is to identify the area of the integral where we get most of the contribution, as in a situation like this. We have to identify that place, that stationary phase point, and then we have, courtesy of some mathematical analysis, which we don't have to do here, we have an expression for the integral that's obtained by looking at just this region. By the way, as I've noted here, this implies reflection. The stationary phase point, 157.5 degrees, is right about here. So that corresponds to the place where we would expect a reflected wave to appear if we were to think of this problem in an optical sense. Now, this isn't an optical problem. This isn't light. This isn't some very, very high frequency electromagnetic radiation. Nevertheless, it appears that we have something that looks somewhat optical going on here. So we often see this kind of behavior whenever Ka is large, whenever the electrical dimensions of the problem are large, and we can identify some part, F sub m, that's slowly varying. Under these conditions, the integrals can be approximated using this thing called the method of stationary phase. And here it is. If you have some integral with endpoints a and b, and some slowly varying part, this is our F sub m, and some quickly varying part, this is our F sub p, and that quickly varying part is varying like a phasor, and we can identify some function gamma as a function of the variable of integration. Then it turns out that we can write this integral to a very good approximation, and this is an approximation to be sure, as this F sub m part evaluated at the stationary phase point, F sub p evaluated the stationary phase point, and then some additional constants. And both of these things depend on second derivatives of this function gamma, which is identified here. So the basic scheme is you get the integral in this form, you identify gamma, you identify the stationary phase point, and then you can compute this integral, or this closed form expression here. Now, how can we find the stationary phase point? Well, we could go back to this method where we plot the slow and fast moving parts, right? But that's, of course, a little bit awkward. What we'd rather have is a mathematical way to do this that would be suitable for a computer code. So the way we do that is by Fermat's law. According to Fermat's law, the stationary phase point is defined by the first derivative of that function gamma that we identified on the previous slide, and where it is a local minimum is equal to 0. So Fermat's law is simply that the stationary phase point is given by the first derivative of this function gamma being equal to 0, that is, gamma being a minimum. So Fermat's law is not quite as arcane as you might first think. It's actually a pretty intuitive idea. One way to say it in words is to say that Fermat's law is the observation that light, which is a form of electromagnetic radiation, follows the path that requires the minimum time to traverse. What does that mean? That means if I have a source over here and then some surface and some field point, well, sure, I've got a direct line of sight. That's a minimum time path. But there's also a minimum time path here. And that minimum time path happens to correspond to optical reflection. In fact, Fermat's observation, as written mathematically here, can be interpreted as Snell's law of reflection. They are, in fact, identical ideas. Snell's law of reflection says that angle of incidence equals angle of reflection. But you can see that choosing angle of incidence to angle of reflection being equal gives you the minimum length path. There is such a thing as Snell's law of refraction, which we won't talk about here, but the idea is that if you have some refractive medium, say like the ionosphere, and electromagnetic radiation is refracted by this refractive medium, then the path it takes also, again, minimizes the time. Okay, so Fermat's law, related to this concept of reflection. In our problem, k times gamma of phi is proportional to propagation time. So k times the first derivative of gamma equal to 0 corresponds to the local minimum satisfying Fermat's law. Thus, the stationary phase point corresponds to the point of reflection in the ray optical paradigm of propagation. In other words, we're seeing where things which we might consider microwave frequencies behaving like light, at least to some approximation. And if things are electrically large and the frequencies are relatively high, then it turns out that we can do things which look very much like optics. People sometimes refer to this whole idea as microwave optics, the idea that in some cases, if you're careful, microwave frequencies can be treated like optical frequencies. So in this problem that I discussed a few slides back, where the angle to the field point was 135 degrees, we could ask ourselves now, what's the easy way to find the stationary phase point, right? We found graphically in a previous slide that it was right there at 157.5 degrees by inspecting the slow and fast-moving parts of the integral. However, we see that by Fermat's law, you can calculate this very, very quickly. That stationary phase point is given by this expression, and it turns out to be 157.5 degrees. Or you could think of this as Snell's law. Any of those techniques for identifying the stationary phase point is fine. So we can compare the stationary phase method to straightforward integral physical optics. So that's what I'm doing. I'm comparing the physical optics solution to the stationary phase evaluation of the physical optics integral. So one method, we're doing integration, and the other method, we're just computing this closed form expression. So again, the same problem that I've been talking about all along. This is the 10 wavelength case. This is the 1 wavelength radius case. What we see in the 10 wavelength radius case is excellent agreement over the whole range where we would expect physical optics to be valid. So let's just be clear what's happened here. We have found a way to compute without integration the physical optics result over the whole range where physical optics is valid. Of course, where physical optics isn't valid, things go wrong the same way. In the 1 wavelength case, where the cylinder is smaller, we expected the physical optics solution to have a smaller range of validity. And in fact, it's true for the stationary phase method as well. And we see they agree with each other relatively well, again, wherever physical optics is valid. Where physical optics isn't valid, we see that they differ by quite a bit, but neither one is valid in that region. So we summarize here, the stationary phase solution is excellent where specular scattering is expected. In other words, where we expect physical optics to give a reasonable answer. I'll just point out one other thing that turns out to be neat about the stationary phase solution. You'll note the physical optics solution oscillates back here, whereas the stationary phase solution goes smoothly to 0. Now, what do you expect to happen physically in this scenario? Well, this is the forward scattering region. So the expected behavior is shadowing. This looks a lot like shadowing, right? I'm not saying it's right. I'm just saying that the way in which it's wrong is more consistent with what we physically expect to happen. And that's a useful feature. It also argues for the interpretation here that stationary phase evaluation is in some form reflection, right? Because we would expect that the reflection goes to 0 as we get deeper and deeper into the forward scattering region. In other words, this whole area here is the forward scattering region. We would expect to see no reflection out there. And that's what stationary phase is telling us. So some other features of stationary phase analysis. Surfaces with multiple inflection points may have multiple stationary phase points, and each one generates its own reflection-like contribution. So an example I might show is a surface like this and a source and field point. Well, we get a specular point or a stationary phase point there. We might get a stationary phase point there. So there's no reason why we can't have multiple stationary phase points, just like we have multiple reflection points. Stationary phase analysis completely neglects the endpoint effects. So let me just show you a picture that's talking about that. When I compute the physical optics integral, I of course have this issue that the currents, the equivalent currents, are truncated at the shadow boundaries. And those shadow boundaries are, as I'm indicating here, this shadow boundary and then this shadow boundary, right? So I get a fraction of a period of this rotating phasor left over from this section here, right? I get lots of cancellation here, but at the very ends, I have a partial period of the spinning phasor. That's an endpoint effect, and it can degrade the quality of the stationary phase analysis. Now, it's usually pretty good, but if you get into a certain situation, like for example, the stationary phase point is too close to one of the endpoints, then things can go wrong. Stationary phase analysis breaks down if the stationary phase point gets too close to the endpoint or to one of the other stationary phase points. In any of those cases, we should be aware that the solution will be degraded. So, concluding remarks. We have seen that the physical optics integral can, in certain cases, be reduced to a closed form expression using the method of stationary phase. This closed form expression appears to be reflection, and in fact it is, at least to the extent that we can have optical reflection at microwave frequencies. Again, the higher the frequency is, or the larger the electrical surfaces are, then the better this whole business becomes. It'll turn out to be extremely useful for the kind of work we want to do with large antennas. Fermat's law specifies a stationary phase point, which you can interpret as being the point of reflection. In a future lecture, we will formalize and extend all of this business as the theory of geometrical optics. One way to think about geometrical optics, or GO as it's frequently abbreviated, is simply it's the asymptotic high-frequency evaluation of physical optics. GEO will turn out to be the fastest, simplest way to compute scattering from surfaces when reflection dominates. But to be clear, GEO will not replace physical optics. We'll have pros and cons that will determine whether one should be used or the other should be used. This concludes this lecture on stationary phase evaluation of physical optics problems.